I'm going to be doing problem 27 from the book, chapter 14, subsection 3. This problem's going to be a problem where we convert from Cartesian coordinates to polar coordinates. I also chose one where there was a sum of two iterated integrals that you had to take into one iterated integral, because we haven't done a whole lot of those. I think it's kind of interesting. It's one of those things where more often than not it's really helpful to write it out to help visualize it. So that is what I do a lot of times. So the boundaries for the first iterated integral we're going to be dealing with are 0 through x for y. So 0, y equals x. And then for x we're going to have 0 and 2. So that's the region that we're going to have bound by the first integral that we're dealing with. And then the second one is going to bring in this purple sliver here. Y is bound by 0 and root 8 minus x squared. So root 8 minus x squared is going to be this arc right here. And then y equals 0, it's going to be right here. So it's the same, I guess, lower bound, if you want to think of it that way. And then the upper bound is what's really going to be giving us the polar coordinates. That's what's going to make this better to deal with that way, since when you add this little slice on, you basically get a section out of a circle. And then the boundaries for x just continues where we left off with the other iterated integral, and then it goes to 2 root 2. So that 2 root 2 is going to be the same as the radius of the boundary that we've got for y. So they meet up right down there. That's going to show us that for the next step, the outer radius that we're going to be dealing with is 2 root 2. So once we've got that all together, we can kind of clean up this graph a little bit and get this. This is the relevant data for the next step. Again, I said that the radius was going to be 2 root 2. Since there isn't a chunk out of here on the inside, it's not like a donut as much as it is a disk. We're going to be coming from the origin. So it's going to be 0 through 2 root 2 for our integration with respect to r. And then our integration with respect to theta is going to go from 0 right here to pi over 4. It's easy to remember. We're always going to be using the lower boundary in the order that it would be progressing through the radian circle. It's probably more confusing than it is helpful, but the idea is that, you know, if you're over here, this is kind of where it gums me up, or becomes important to me. If we're going to be dealing with a lower bound for another integration where the angle that we're dealing with is pi over 2, and then we've got pi, our lower value is always going to be that pi over 2. So a little bit of a sidetrack, but it's kind of important. So now that we've got this, we can throw it together into one iterated integral in polar coordinates. So here we go. There's that. So again, our boundaries for dr are going to be 0 through 2 root 2. See that right there. And then our boundaries for d theta are going to be 0 through pi over 4. And then the actual function that we're integrating is going to be root r squared times r, which we're going to simplify in a second, but it's easier in this form to see exactly where we're getting that. Now, we know that x squared plus y squared thrown into polar coordinates or converted to polar coordinates is always going to be r squared. That's because r squared cosine theta plus r squared sine theta simplifies out to just r squared. And then, since we are converting to polar coordinates, it's important to bring that extra r in there. So, when we simplify that, we get this. So, it's a very simple function that we're actually integrating once we convert it to polar coordinates. And from there, it is just a matter of integrating it, which shouldn't be too hard. So start off by integrating in terms of r. Then once we evaluate that, we get this right here. And then all that we have left is to integrate in terms of theta. Again, pretty simple. And then we have our answer. So these steps I went over a little bit quickly, but they should be pretty simple. The real meat of the problem for this one is this step right here, bringing the sum of these two iterated integrals into this, and then bringing this into the integral that we can evaluate in polar coordinates. So again, this is our answer. Hope it was at least a little helpful. And that's it. Thank you.